Chapter 15, Quantum Translation, Section 15.1, the free particle. The time-dependent Schrödinger equation is each psi equals IH bar delta psi over delta t. The wave function of a one-dimensional particle is a function of two variables, the position x and time t. The time-dependent Schrödinger equation of a one particle is therefore each psi of x and t equals IH bar delta psi over delta t. Again, this psi is a function of the position x and time t. But if the potential energy V of the 1D particle never changes over time, we have Vx as the potential energy. Since the Hamiltonian operator is the sum of the kinetic energy operator and the potential energy operator, we have this equation as the time-dependent Schrödinger equation. On the right-hand side, we have IH bar delta psi over delta t. On the left-hand side, we have simply the kinetic energy operator applied to psi plus potential energy operator applied to psi. The wave function of the particle depends on its position and time, but we can separate the two variables by setting psi to be a lowercase psi of x only and a function of time, and this will simplify the time-dependent Schrödinger equation. So mostly we replace this uppercase psi with the product of the lowercase psi and a function of time here and here and finally here. Because the function of time does not depend on x and the function of x does not depend on time, we can simplify this equation. So over here we can take this function of time out of the second derivative, and over here we can take this function of x out of the first derivative with respect to time. So this lowercase psi of x is considered a constant with respect to time. It does not depend on time. Now the separation of the variables leads to this time-dependent Schrödinger equation. The separation is done this way. We assume the uppercase psi, the wave function of x and t, can be expressed as the product of the lowercase psi of x only times the function the lowercase psi of x only multiplied by a function of time. So now we have this time-dependent Schrödinger equation. We can now divide both sides by psi of x and f of t. Now we have this equation. So on the left-hand side, we have negative h bar squared over 2m psi delta squared psi over delta x squared plus vx. On the right-hand side, we have IH bar and then 1 over f times delta f over delta t. And why do we do this? When we do this, we can see on the left-hand side of the equation, we have a function of x and x only. This part does not depend on time. And on the right side, we see a function of time which does not depend on x. If the left part does not depend on t, the right side does not depend on x, and we have equal sign between. That means both the left side and the right side are independent of x and t. Alright, that means we can say the left equals the right equals a constant. So now we're going to use a symbol E, a letter E, to denote that constant, because later you will see that constant has a physical meaning, which is the energy of the system, and therefore we use this letter E to denote that constant. Again, the left side does not depend on t, the right side does not depend on x, and they are equal. Therefore, both sides are independent of t and x. Alright, now we're going to just say, well, the left side equals the right side equals E, and E has a physical meaning. It's the total energy of the system. And now we have actually two differential equations. This function of x is equal to E, and this function of t is equal to E. So we write out these two equations here and here. Given this equation, we can move around the variables so that df over f is equal to negative IE over h bar. So you just move this IH bar to the right hand side, you move the delta t to the right hand side, and then we have this equation. Again, df over f is negative IE over h bar times dt. This is a simple differential equation. To solve this equation, we just need to integrate both sides. We get the logarithm of f is equal to negative IE over h bar times t, and therefore this f function is e to the power of negative IET over h bar. It's an exponential function of time. In this case, the probability distribution of the particle is independent of time, because the probability density is this psi times f squared, and we can separate this two. It's psi squared and f squared. Now let's look at this f squared. It's really the squared modulus of f, which is the complex conjugate of f times f. Over here we have f, and then what is its complex conjugate? We just need to replace I with negative I. Now we have the complex conjugate here. We do the multiplication, we get 1. That means the squared modulus of f is always 1. This part is always 1. The probability density of the particle never depends on time. It never changes with time. So now we have this time independent equation for the 1D particle over here. And both sides multiplied by the psi of x. This time independent Schrodinger equation becomes over here the kinetic energy operator, negative h bar squared over 2m d2 d squared over dx squared applied to psi, plus the potential energy applied to psi is equal to E psi. The simplified form of the time independent Schrodinger equation for the 1D particle is simply h psi equals E psi. Psi is a function of x. H is the kinetic energy operator plus the potential energy operator. E is the total energy of the system. Psi of x is the time independent wave function of the particle. The squared modulus of psi is the probability density of the particle at position x. The potential energy of a free particle is always 0. So in this case, for a free particle, V is always 0. Therefore, we have the kinetic energy operator applied to psi equals E psi. And then we can move around those parameters. Then the second derivative of psi is equal to a constant times psi. That constant is negative 2me over h bar squared. We can simplify this expression by defining k to be the square root of 2me over h bar squared, or the square root of 2me over h bar. This k is a constant because E, the energy of the system, is a constant for the time independent Schrodinger equation. The mass is of course a constant. And then this is also the magnitude of the momentum, because in this case for a free particle its total energy is the kinetic energy. So the square root of 2me is the square root of 2m times the kinetic energy, which is half mv squared. We do some evaluation here, we get mv, which is just the magnitude of the momentum. Therefore kh bar is the magnitude of this momentum. So you can see over here, this is k is the magnitude of the momentum over h bar, and the momentum is k times h bar. Now we have this equation, which is simpler. the second derivative of psi is equal to psi multiplied by negative k squared. There are two possible solutions for this kind of differential equation. Again, the second derivative of psi is psi multiplied by a constant, negative k squared. And we have two solutions, e to the power of plus ikx and e to the power of negative ikx. We can easily verify that these two solutions satisfy this differential equation. We can take the second derivative of e to the power of plus ikx. We will get plus ik times this exponential function. And of course, plus ik times plus ik is negative k squared. We can also take the second derivative of e to the power of negative ikx. We'll get negative ik times this e to the power of negative ikx. And of course, negative ik times negative ik is also negative k squared. So we just verified that the psi plus and psi minus are both legitimate solutions to this differential equation. However, there are actually an infinite number of solutions. The general solution for a free particle is a linear combination of psi plus and psi minus. It can be expressed as a coefficient times e to the power of plus ikx plus a coefficient times e to the power of negative ikx. We use a sub plus and a sub minus to denote those coefficients. They can be any constant. They can be complex numbers. In general, if two functions f and g are both eigenfunctions of the same operator O with the same eigenvalue, then the linear combination of these two functions, that means a coefficient times f plus a coefficient times g, is also an eigenfunction of that operator, and a and b can be any constant. So over here we provide a linear combination of two eigenfunctions for the same operator, and they have the same eigenvalue. Then af plus bg is also an eigenfunction of this operator, also with the same eigenvalue. So specifically, since this is an eigenfunction of the Hamiltonian, this is also an eigenfunction of the same Hamiltonian, and these two have the same eigenvalues, negative k squared, and therefore the linear combination of these two exponential functions is also an eigenfunction of the same Hamiltonian with the same eigenvalue, negative k squared. The general solution for a free particle is the linear combination of psi plus and psi minus. Psi plus is e to the power of plus ikx, psi minus is e to the power of negative ikx. In front of the exponential functions, we have coefficients. These two coefficients can take any values. They are just arbitrarily constant. Now let's verify it. We'll take the second derivative of this general solution. So over here, the second derivative of this part plus the second derivative of this part. Over here, we just copy this function over here, and then since we're taking the derivatives of an exponential function over here, we need to copy this exponential coefficient twice, plus ik here and plus ik again. Over here, same, negative ik and negative ik, so two times. Positive ik squared is negative k squared. Negative ik squared is also negative k squared. So overall, we have just negative k squared times psi. Psi is the linear combination of these two. And now we just proved that h being applied to psi is equal to, well, negative h bar squared over 2m times the second derivative of psi, which is negative k squared psi. Now this is simple multiplication. We have k squared h bar squared over 2m times psi on the right side of the equation. Again, h psi equals e psi, and over here k squared h bar squared over 2m is the energy of the system. So we have just verified the linear combination of e to the power of plus ikx and e to the power of negative ikx is also an eigenfunction of the Hamiltonian operator for the one-dimensional free particle, regardless of the values of a sub plus and a sub minus. and the eigenvalue over here, k squared h bar squared over 2m, is both the total energy of the system and also the kinetic energy of the system. Because the system is a free particle has a zero potential energy. We can also determine the momentum for e to the power of ikx and e to the power of negative ikx. We just need to apply the momentum operator to these eigenfunctions, and over here, when we apply the momentum operator to e to the power of ikx, we get this wave function multiplied by kh bar. Therefore, the momentum for this eigenfunction is kh bar. We apply the momentum operator to e to the power of negative ikx, we get negative kh bar times this exponential function. The eigenvalue is negative kh bar. That indicates the system with this wave function has a momentum of negative kh bar. But now if we have a general solution over here as a linear combination of e to the power of positive ikx and e to the power of negative ikx, that means this particle has a momentum of kh bar and negative kh bar at the same time. This free particle can be moving forward and backward at the same time.